with respect to 4.4. What is the rectified type instruments? That is electronic AC voltmeter and types of rectified type AC voltmeters. Okay, these concepts I discussed. Okay, then you'll see in this session I want to discuss as a 4.5 as a, in this 4.5 one concept that I want to discuss, amplifier type instruments. Amplifier type instruments. Okay, amplifier type instruments. The another one is electrostatic voltmeter. Before that, electrostatic voltmeter. Electrostatic voltmeter. Another one is thermal instruments. Thermal instruments. Mainly I want to cover these topics, but here with respect to these instruments, not in detail analysis is not required. That's why only for who are preparing for engineering service exams, descriptive point of view only, in detail analysis is required. But for objective point of view, not required for in detail analysis. That's why in the chapter 4.5, I am discussing these instruments: amplifier type instrument, electrostatic voltmeter and thermal instrument. I am giving a brief discussion only. Okay, briefly I am explaining that is not required. But who are preparing for IS descriptive point of view, particularly, then you see in miscellaneous concept, there is we are providing in electrical and electronic measurements itself some miscellaneous concept that is not important for various competitive point of view, only that is important for IS descriptive point of view. In that you refer in detail what is the analysis, what is the derivation, all this that you will see. Okay, but here for objective point of view, not required any in detail analysis. That's why I am giving only brief discussion. Then after this, explaining all these amplifier type instrument, electrostatic voltmeter and thermal instrument briefly, then finally I will give some observation with respect to voltmeter and ammeters. With that, chapter 4 will be complete. In the next session, based on this amplifier type instrument, electrostatic voltmeter, thermal instrument, okay, then we'll solve some classroom workbook questions also. Okay, including EDM instrument and 4.3, 4.4 and 4.5. 4.3, 4.4, 4. I given classroom workbooks till now up to 4.2 only. 4.3, 4.4, 4.5. In one session I will discuss that classroom workbook. Okay, but here in this session I am discussing amplifier type instrument, electrostatic voltmeter, thermal instrument briefly. Okay, first we will start with amplifier type instruments. First we will start with amplifier type instruments. Yes, this amplifier type instrument, with respect to amplifier type instrument, I am discussing it is also called electronic DC voltmeter. Yes, electronic DC voltmeter. Yes. Already for measurement of DC voltages, more accurate instrument, more sensitive instrument, PMMC is there. Then what is the need of this electronic DC voltmeter? Why you are implementing this electronic DC voltmeter? That you concentrate. Already for measurement of DC voltages, the more accurate instrument, PMMC is there. Then high sensitivity instrument is also there. What is the need of using this electronic DC voltmeter? Yes, no doubt at all, PMMC is the high sensitivity and more accurate instrument. But the problem with PMMC is, for example, I want to measure the voltage across 10 ohm resistor. I told already, to reduce the loading effect, we can use the minimum input resistance of voltmeter must be 10 times. RV must be 10 RL. That's why to measure the voltage across 10 ohm resistor, we can use 100 ohm voltmeter. No problem. We can design 100 ohms. Okay. Then I want to measure the voltage across 100 ohm resistor. Then we can use the minimum input resistance of voltmeter must be 1000 ohms. Why? To reduce the loading effect. Okay, we can design the voltmeter with 1000 ohms also, no problem. Now I want to measure the voltage across 1000 ohms. Then we can design the voltmeter with a minimum input resistance of 10,000 ohms. 10,000 ohms means we want to design with 10 kilo ohms. Understood? Then up to this it is okay. You can measure voltage across 100 ohms. We can design the voltmeter with 1000 ohms. Then we can design the voltmeter with 10 kilo ohms, no problem. But if you want to measure the voltage across 10 kilo ohms, then we can design the voltmeter with the minimum input resistance of 100 kilo ohms. Why? In order to reduce the minimum must be 10 RL to reduce the loading effect. But up to this it is okay. But designing this voltmeter with a very high input resistance is practically difficult. That's why I'm not designing with 100 kilo ohms is not possible. That's design of PMMC voltmeter with 100 kilo ohms is not possible. That's why I'm using only 10 kilo ohm voltmeter only to measure the voltage across 10 kilo ohms. When I'm using 10 kilo ohm voltmeter to measure the voltage across 10 kilo ohm means then it offers the error of, I told already, if RV equal to RL, error equal to minus 39.9% loading error we can get. Okay, that is a problem with PMMC voltmeter. That means no doubt at all, PMMC is high sensitivity, high accuracy, less loading effect up to some loads only. If the same PMMC is used to measure the voltage across high resistive loads, it offers less sensitivity, and more loading effect. Okay, that is the problem with the PMMC. Then to overcome this problem, we want to design this voltmeter with a high input resistance. But directly we can't design a voltmeter with high input resistance. For that, what we are doing means, directly we are not designing. That's why in front of PMMC, we are placing one amplifier. In front of PMMC, now we are designing like this to measure the voltage across high resistive loads. In front of PMMC, we can use one amplifier. Okay. Then this internal it consists of PMMC, no doubt at all, PMMC voltmeter. Now we know that amplifiers will offer high input resistance in the range of mega ohms also. Clear? Once amplifiers will offer high input resistance, this total combination will offer high input resistance. No? Yes or no? Once this total combination will offer high input resistance, if it is used to measure the voltage across high resistive loads also, then loading effect is less, sensitivity is more. Whatever the drawbacks are, that can be overcome. Understood? That's why in front of PMMC we can use one amplifier. That's why it is called amplifier type voltmeter. Why do go for this? Reason that I told. Okay, amplifier type voltmeter. Amplifier is one electronic device. That's why it is also called electronic DC voltmeter. It is electronic elements we are using, and our voltmeter is a DC voltmeter. That's why it is electronic DC voltmeter. Clear? Okay, that is the reason why you go for the electronic DC voltmeters. Understood? Okay, write down. If the PMMC is used to measure the voltage across high resistive loads, it offers more loading effect and less sensitivity. I am telling that with respect to high resistive loads only. It offers more loading effect and less sensitivity. More loading effect and less sensitivity. To overcome this drawback, it is required to design the voltmeter with high input resistance. It is required to design the voltmeter with high input resistance. For that, a PMMC is placed. For that, an amplifier is placed. An amplifier is placed in front of  This combination is called electronic DC voltmeter. Yes, this combination is called electronic DC voltmeter. Okay. Now see what is the block diagram representation of electronic DC voltmeter. I am discussing amplifier type instrument, means I am discussing the electronic DC voltmeter. This is electronic DC voltmeter. Yes. Now see the block diagram representation. It consists of one amplifier at input side, this is one amplifier, yes, the output of the amplifier is given to PMMC. Internally electronic DC voltmeter is also consist of PMMC. Because of internal it consists of PMMC, what type of damping you can use in electronic DC voltmeter? Eddy current damping, because of permanent magnet. So this is PMMC. Yes. This total combination is used to measure the voltage across high resistive loads to reduce the loading effect. Then what the PMMC measures? This PMMC measures average value. Again, this no need to convert RMS value. But in electronic AC voltmeter, I converted this average value into RMS value because it is a AC voltmeter. But it is a DC voltmeter. Directly you can measure the average only. Again, no need to convert into RMS. Then this is about electronic DC voltmeter. This is a block diagram. This RL is the load resistance. Okay, this is the block diagram representation of electronic DC voltmeter. Okay. Now this combination is used to measure the voltage across high resistive load. Amplifier will offer high input resistance. This total combination will offer high input resistance. Then loading effect is reduced. Clear? Now see, based on the type of amplifier we are using, we can design different types of electronic DC voltmeters. Okay. We know that op-amp is used as an amplifier. Op-amp is used as an amplifier. Then that voltmeter is called op-amp voltmeter. Op-amp voltmeter. That means, again no need to tell op-amp electronic DC voltmeter. You can ready to identify op-amp voltmeter is the one of the electronic DC voltmeter. It consists of op-amp at input side. We can also use FET as amplifier. If FET is used as amplifier in this, then that is called FET input voltmeter. Then it is called FET input voltmeter. That is called FET input voltmeter. Next. We know that BJT is also used as an amplifier. But BJT again in different configuration. Here based on type of amplifier we are using, we can design different types. Electronic DC voltmeter. The design procedure I am not giving. Just introduction points only I am giving. Okay, I told already. Okay, BJT is used in CE configuration. Then that electronic DC voltmeter is called transistor voltmeter. Yes, transistor voltmeter. Next, it is also used in CC configuration. Then that electronic DC voltmeter is called emitter follower voltmeter. Yes, emitter follower voltmeter. Emitter follower voltmeter. It is also used in emitter coupled configuration. Yes, emitter coupled configuration. That electronic DC voltmeter is called difference voltmeter. Difference voltmeter. Difference voltmeter. But point to remember, All these voltmeters are which voltmeters? Electronic DC voltmeters only. All these are electronic DC voltmeters. But based on the type of amplifier we are using, we can design different types of electronic DC voltmeter. For example, I am using BJT as an amplifier in CE configuration like this. This output of this amplifier is given to PMMC. This is one way to implement the voltmeter like this. BJT is used as an amplifier in CE configuration. This output is given to PMMC. Let the meter resistance is RM. Now this total combination is used to measure the voltage across the load. To measure the voltage across the load, this combination is used. Then it must require compulsory plus VCC for biasing. Okay, this is one electronic DC voltmeter. This amplifier used in CE configuration. Then this voltmeter is called transistor voltmeter. Transistor voltmeter means, again no need to tell, transistor electronic DC voltmeter. You can ready to identify transistor voltmeter is the one of the electronic DC voltmeter. Yes, it consists of BJT at input side in CE configuration. Emitter follower voltmeter is also one of the electronic DC voltmeter. It consists of BJT at input side in CC configuration. That is it. Like this, we can design different types of electronic DC voltmeter. If we compare these electronic, I am comparing this electronic DC voltmeter. Now among all these electronic DC voltmeter, which voltmeter is highest input resistance? Op-amp electronic DC voltmeter is highest input resistance. The next one is FET input voltmeter. The next one is emitter coupled, that is emitter coupled voltmeter. The next one is transistor voltmeter. Sorry, emitter follower voltmeter. The last one is transistor voltmeter is less input resistance. Okay, this I am comparing only in the electronic DC voltmeters. Then what about the sensitivity? Then sensitivity of op-amp voltmeter is greater than sensitivity of FET input voltmeter is greater than sensitivity of emitter coupled voltmeter is greater than sensitivity of emitter follower voltmeter is greater than sensitivity of transistor. Then if the sensitivity is more, we know that loading effect is less. Then loading effect due to loading effect due to op-amp voltmeter. If the sensitivity is more, loading effect is less. Then loading effect due to FET input voltmeter. Then loading effect due to emitter coupled voltmeter. That is a difference voltmeter. Loading effect due to emitter follower voltmeter. Loading effect due to transistor voltmeter. Okay, this is the internal comparison with respect to electronic DC voltmeters. Electronic DC voltmeters. Okay. Now I want to compare this electronic DC voltmeter with other voltmeters. This internal comparison already know. Now you take electronic DC voltmeter. Now among all the voltmeters, highest sensitivity is electronic DC voltmeter. Electronic DC voltmeter is in this voltmeter, any voltmeter. But internal comparison you already know. Electronic DC voltmeter. The next highest sensitivity is SDC. That is the sensitivity of PMMC. DC sensitivity means that is the sensitivity of PMMC. Okay. Next, AC sensitivity of full wave rectifier voltmeter. The next one is AC sensitivity of half wave rectifier voltmeter. The next one is sensitivity of MI, sensitivity of EDM. The least sensitivity is sensitivity of ESP, electrostatic voltmeter. Okay, this is a final comparison with respect to sensitivity. If the sensitivity is more, what is the loading effect? The loading effect due to electronic DC voltmeter. All these voltmeters are electronic DC volt. Less than loading effect due to PMMC, that is a DC voltmeter, is less than loading effect due to full wave rectifier voltmeter. Yes, loading effect due to half wave rectifier voltmeter. Yes, loading effect due to next MI instrument. Loading effect due to EDM instrument. Loading effect due to ESV. Highest loading of effect is offers the electrostatic voltmeter. Okay, this about the final comparison of different instruments based on sensitivity with respect to sensitivity and with respect to loading effect. Okay, like this we can define any electronic DC voltmeter. Clear? Understand? That you concentrate. Okay, mainly these points you remember. Now tell me, what is the advantages of electronic DC voltmeter? Advantages of electronic DC voltmeter. Yes, one is used for both AC and DC. We can use for both AC and DC. Even the electronic DC voltmeter, it is used for both AC and DC. Yes, high sensitivity, high input resistance. Yes, high input resistance. Another one is less loading effect. Less loading effect. Okay, these are the advantages of electronic DC volt. Electronic DC voltmeter in the sense amplifier type instrument. What is the disadvantages? Disadvantages of electronic DC voltmeter. Tell. Here we are using, at input side we are using amplifier. Which device are used as amplifiers? We know that solid state electronic device are used as amplifiers. Solid state electronic device are used as amplifiers. We know that solid state electronic device are more sensitive to temperature. That's why the total meter is sensitive to temperature. That is, this meter is because of SSC, solid state electronic device. Means semiconductors are more sensitive to temperature. Because of SSC, it is more sensitive to temperature. Easily, because of change of temperature, the meter reading easily changes. It is more sensitive to temperature. Okay, this one point to remember. But point you remember here, for example, I want to measure the voltage across any load. Let this is supply. I want to measure voltage across any load. I am using PMMC. Directly I will connect the PMMC like this. Then whatever the input we are giving, that input is enough to operate this PMMC voltmeter. Again, no need of any external supply for this. Yes or no? But when I use this meter, this is one of the electronic DC voltmeter. This is one of the electronic DC voltmeter. Yes. If you use this meter to measure the voltage across the loads, here we are giving some supply. Let this is the input supply. Along with the input supply, it requires some external supply also for biasing. Otherwise, this meter will not operate. That's why it requires external supply or biasing voltage for its operation. Which of the following voltmeter requires external supply for its operation? Electronic DC voltmeter requires external supply for its operation. That is, it requires biasing voltage or external supply for its operation. Because of plus VCC. Okay, these are the drawbacks of electronic DC voltmeter. Okay, these points you remember to answer mainly theory question. In classroom workbook, based on this, one model of problem also I will solve. That you will see. Okay, this about in detail. Here I am not. Then in detail discussion of electronic DC voltmeter means how to design each voltmeter. That is in detail discussion. Okay, that is not required for objective point of view, only for descriptive point of view only important. How to design op amp, FET input, transistor, emitter follower, difference voltmeter, all this is in detail discussion. That is not required here. Clear? Understand? Then you go for another voltmeter in this concept. See, one of the point to remember, VTVM is one of the electronic DC voltmeter. write as a note, VTVM is one of the electronic DC voltmeter. This is vacuum tube voltmeter. VTVM stands for vacuum tube voltmeter. Vacuum tube voltmeter is one of the example of electronic DC voltmeter. Okay, that point also remember. See, not only amplifier type instruments, practically we are using amplifier, rectifier type instrument, rectifier and amplifier type instruments also we are using. This amplifier type instruments, rectifier amplifier type instrument, amplifier and rectifier type instruments, these are all our milliampere and microampere ammeters. You can, in order to measure the milliampere and microampere, then mainly you can use this type of meter. Amplifier, rectifier and amplifier type instruments, all these. That is, if you want to measure very low currents or low voltages, mainly low voltages, we can use these voltmeters. To sense the very small currents, also, we can use these meters. Next, write as a electrostatic voltmeter. In 4.5 itself, I am discussing electrostatic voltmeter. Yes. Yes. Listen please. I told already, to measure very high voltages for any type of waveform, it may be sinusoidal or non-sinusoidal, it may be DC or AC. For any type of waveform to measure very high voltages, we can use electrostatic voltmeter. For any type of waveform, that is, for any type of waveform, to measure very high voltages, that is up to 500 kV. We can measure up to 500 kilovolts also. ESV is used. Electrostatic voltmeter is used. Then it is used for both AC and DC. This is already given even in the tabular column also. In the basic requirements of in the fundamentals of indicating type instrument, in the tabular column also I already given this. It is used for both AC and DC. Next, it is RMS measuring and RMS. Whatever the input we can apply, it measures RMS values. Yes, it is RMS measuring and RMS indicating type instrument. Okay. But what is the principle of electrostatic voltmeter? The principle of electrostatic voltmeter is, it works on the principle of attraction, that it works on the principle of electrostatic effect, that is attraction force between the two plates. It works on the principle of electrostatic effect. Yes, it works on the principle of electrostatic effect. Okay, that is attraction force between the two plates. We don't have any repulsive principle in the case of electrostatic instrument. But attraction and repulsion is there only in MI instrument. But in the case of electrostatic instrument, only attraction principle only. Okay. Then that is attraction force between the two plates due to applied voltage. Then mainly these are broadly classified into two types. One is a parallel plate electrostatic voltmeter, parallel plate electrostatic voltmeter, and another one is a circular plate electrostatic voltmeter. Okay. Then with respect to parallel plate electrostatic voltmeter means, with respect to parallel plate electrostatic voltmeter, okay, it consists of two plates like this. One is a fixed plate, another one is movable plate. For this movable plate, we are applying the controlling torque, that is a spring control. Here we are using helical springs because of parallel plate electrostatic voltmeter. In this case, the controlling force Fc equal to Kx. This one is fixed plate. Now we are applying the voltage across these two plates. Whenever voltage across, this is fixed plate. Another one is movable plate. Whenever voltage is applied like this, then plus in outer side of the plate this is plus, but inner side opposite charge is induced. This concept you know in the capacitor. Okay. Then this is negative at outer side. In inner side of the plate opposite charge is induced. Now on this we are placing the pointer arrangement. Can place like this. Then whenever controlling torque equal to deflecting torque, then the pointer comes to the steady state. In a parallel plate electrostatic voltmeter, you can take the displacement only. Okay. Then tell me. Then between two opposite charges, attraction force is produced. Because of this attraction force, this is a movable plate. Movable plate. Then plate is moving like this. Then controlling torque is acting like this. Whenever these two torques are equal, then the pointer comes to steady state. Okay. Now, what is the force produced? What is the deflecting force produced in parallel plate electrostatic voltmeter? Half V square dC by dx. Okay, this is the deflecting force produced in the case of parallel plate electrostatic voltmeter. Then what is the controlling force? Fc equal to Kx. Then if the pointer is at steady state condition, yes, at steady state, Fc equal to Fd, then Kx equal to half V square into dC by dx, then x equal to 1 by 2k V square into dC by dx. Okay, this is the displacement. Like this we can get. Then what the capacitance here? C equal to A epsilon by D, that is A epsilon naught into epsilon R by D. What is epsilon naught here? Permittivity of free space. The value of epsilon naught equal to 8.854 into 10 to the power of minus 12 farad per meter. Okay, this one formula you remember. This is with respect to parallel plate electrostatic voltmeter. Now if you see with respect to circular plate electrostatic voltmeter, circular plate electrostatic voltmeter, here you take not the linear displacement, you can take the angular displacement. Then what is the deflecting torque Td equal to? Then what is the deflecting torque? This is very important formula. Yes, I am not giving derivation, no need of that. Deflecting torque Td equal to half V square dC by d theta. Half V square dC by d theta. Then with respect to deflecting torque at steady state, yes, at steady state, Tc equal to Td, then k theta equal to half E square dc by d theta. Then what is theta equal to 1 by 2k V square into dc by d theta. Okay, this is important. This formula you remember, and this formula also you remember. Theta equal to 1 by 2k V square and dc by d theta. If dc by d theta equal to constant, then theta is proportional to V square. Then in electrostatic voltmeter also scale is non-linear. Scale is non-linear. Okay, this about with respect to circular plate electrostatic voltmeters. Yes, quick note down. Yes. But in circular plate electrostatic voltmeter, based on operation, again these are mainly classified into two types. One is a quadrant type electrostatic voltmeter, attracted disc type electrostatic voltmeter. These are again classified into two types. One is quadrant type. Yes, quadrant type electrostatic voltmeter. Another one is attracted disc type electrostatic voltmeter. Disc type electrostatic voltmeter. These are used 100 volts to 20 kV. Then these are used up to 500 kV. Up to 500 kV. Okay. This based on the voltages we are measuring. These are attracted disc type electrostatic voltmeters are used for very high voltage applications. Then how to extend the range of electrostatic voltmeter? Write down as a note. The range of electrostatic voltmeters is extended by using, one is resistive potential divider arrangement, resistive potential divider arrangement. This one point to remember, arrangement. This one method we can use, and one more method is, resistive potential divider arrangement method is used for both. This method is used for both AC and DC. Both AC and DC. Okay. Then one more method is using series capacitors to extend the range. Using series capacitors. Okay. These are used only for AC. This method of extension of range is only for AC. But electrostatic voltmeter is used for both AC and AC. No doubt at all. But it is used only for AC. This method, extension of range method, is used only for AC. Now, in the second method, to extend the range, for example, to extend the range from VM to V, then how much series capacitance? The capacitance connected, the series capacitance connected. The series capacitance, directly I am giving, no need of derivation. The series capacitance CS equal to Cm by M minus 1. This formula you remember. This much of capacitance we can connect. Where Cm equal to meter capacitance, internal meter capacitance. Because internally it is electrostatic effect. This is meter capacitance. Then where m equal to multiplying power or multiplying factor. This is multiplying power, or it is also called multiplying factor. Okay, like this we can extend the range of electrostatic voltmeter. Yes, quick note down. Yes. Now tell me, what is the advantage of electrostatic voltmeters? Yes, this over. Can you tell me what is the advantage of electrostatic voltmeter? I told already, to measure very high voltages for any type of waveform, we can use the electrostatic voltmeter. This is one advantage. Okay, advantage of electrostatic voltmeter. To measure for any type of waveform, to measure very high voltages, we can use electrostatic voltmeter. That is one advantage. The second advantage is, these are free from, these instruments are, free from waveform errors, comma, stray magnetic field errors, that is external magnetic field errors, stray magnetic field, comma, hysteresis and eddy current errors, because there is no any magnetic field here. These are free from waveform errors, stray magnetic field, comma, hysteresis and eddy current errors. That's why, because of all the errors are free, all the errors are less in the case of electrostatic voltmeter. That's why these are designed with high grade accuracy. That is first grade accuracy. These instruments are designed with high grade accuracy or first grade accuracy. Okay, these are the main advantage of electrostatic voltmeter. Then mainly with respect to disadvantage point of view, what are the disadvantages of electrostatic voltmeter? Among all the voltmeters, among all the instruments, these instruments are high cost, less sensitivity. These are costly instruments, less sensitivity, more loading effect. These are the main problems with the electrostatic voltmeters. Even large size also, the voltmeter size also very large with respect to electrostatic voltmeter. Okay, these are the main points you remember with respect to advantage and disadvantage. Here I am telling that less sensitivity. Most of the electrostatic voltmeter we can use very low voltage cannot be measured. Minimum of 100 to 500 only we can, minimum of 100 to 500 volts. Okay, starting I am telling that minimum voltage. We can't measure 10 volts, 5 volts by using electrostatic voltmeter because of less sensitivity. But there is a one specially designed voltmeter is the electrostatic voltmeter, Kelvin multicellular voltmeter. By using that voltmeter we can measure minimum voltage of 30 volts we can measure. That is using Kelvin multicellular voltmeter. Kelvin multicellular electrostatic voltmeter, we can measure minimum voltage of 30 volts to 50 volts we can measure. Minimum voltage. Okay, maximum is we can measure up to kilovolts. Minimum is we can measure that. This is having high sensitivity. In this electrostatic instrument, which electrostatic voltmeter is a high sensitivity is Kelvin multicellular. But generally it is a low sensitivity instrument. Electrostatic instruments are low sensitivity instrument. But in that, if you want to measure very low voltages using electrostatic voltmeters, we can use this Kelvin multicellular electrostatic voltmeters. Okay, these points you remember. Yes. Okay, this about the points you remember with respect to electrostatic instruments. Remaining thermal instruments also I want to give 1 or 2 points. Output siding thermal instruments. Yes. The thermal instruments. Yes. These thermal instruments are also used for both AC and DC. Used for both AC and DC. And these are more preferable to measure yes, voltage, current and power at RF range, RF frequency range. To measure the voltage, current and power at radio frequency range, we can use these thermal instruments. This is one of the special applications of thermal instrument. Radio frequency range means in megahertz frequency. At megahertz frequency, up to 50 megahertz or 100 megahertz frequency, if you want to measure the voltage, current and power, we can use the thermal instrument. In thermal instruments, so many instruments are there. One is a hot wire meter. Another one is bolometer, thermocouple meter. Okay, thermocouple meter. Okay, hot wire meter, bolometer and thermocouple meter. Okay, we are using this type of thermal instruments. These are all the thermal instruments. 1 or 2 points you concentrate on hot wire meter. Yes, hot wire meter means in this hot wire meter a wire is stretched between the two contacts and a current is allowed through this wire. Whatever the current we are measuring, that current is allowed through this wire. Then whenever current is allowed through this wire, because of heating effect, thermal instruments are works on the principle of thermal effect or temperature effect. Whenever current is allowed through this wire, because of heating effect, then a sag is formed. Because of heating effect, a sag is formed. Okay, and there is some pointer movement on the scale, and we are providing some controlling torque also. This is a deflecting torque and this is the controlling torque. That means whatever the current you want to measure, if that current is allowed through this wire, because of thermal effect or temperature effect, a sag is formed, then there is a deflection of a pointer. That is the main of. That's why it works on the principle of temperature effect or thermal. That means it works on the principle of flow of change of length of wire due to flow of current being measured. It works on the principle of yes, change of length of wire due to flow of current being measured. Okay, this is the main principle. But whatever the wire we are using, this wire is made with platinum iridium material. This is made with the platinum iridium material. This hot wire is made with platinum iridium material. Okay, in these instruments also scale is non-linear. Theta is proportional to I square. This all the thermal instruments also RMS measuring and RMS indicating type instrument. Whatever the input we can apply, it measures the RMS value. Electrostatic instruments also RMS measuring. Even thermal instrument, it may be hot wire meter or thermocouple meter also, it is RMS measuring and RMS indicating type instrument. Okay, that point to remember. It is also used for, every thermal instrument is used for both AC and DC. But for example, let assume that here I am giving one small formula. Let L equal to length of the wire, L equal to length of the wire, length of the wire, delta L equal to change in length, change in length, delta L equal change in length. Then we can define how much sag is formed. Sag equal to, sag S equal to, how to define the sag? Then we can get sag equal to square root of L into delta L by 2. Then we can define magnification factor. We can define magnification factor. Magnification factor. The magnification factor M equal to sag per unit change of length is called magnification factor. If we simplify this one, we can get L by 2 into delta L. This is the magnification factor. These two formulas you remember with respect to hot wire. But because of high power consumption, less overload capacity, nowadays these instruments are outdated. We are not using this instrument nowadays. These instruments are having high power consumption and less overload capacity. We can measure maximum current of 5 amperes only by using hot wire meter. We can't measure the very high current. We can measure maximum current of 5 amperes, and by using the series resistance in series with meter, we can measure the voltage up to 100 volts only. Okay, that is the voltage and currents we can measure by. If allow the high currents, there is a high, because of heating effect, the wire may be damaged. That's why you can't measure very high currents by using hot wire meter. Okay, but these instruments are outdated. But only advantage of these instruments is we can use at a RF frequency, high frequencies only we can. This is the only advantage of this hot wire meter. Generally, thermal instrument is main advantage is that one. But accuracy is less, and because of high power consumption is high, less overload capacity. One more point to remember, because it works on the principle of thermal effect or temperature effect, these instruments are not affected by stray magnetic fields. Hot wire meters, in general, thermal instruments are not affected by stray magnetic field errors and waveform errors. Thermal instruments are not affected by waveform errors and stray magnetic field errors. Okay, this one more thermal instrument is thermocouple. Thermocouple. Okay, thermocouple instrument. Then it works on the principle of Seebeck effect. It is also used for both AC and DC. Thermal instruments are used for both AC and DC. It is also RMS measuring and RMS indicating type instrument. This works on the principle of Seebeck effect. What is Seebeck effect? I already given in the starting of voltmeter and ammeter. Principle of Seebeck effect. Okay, it works on the principle of Seebeck effect. Then we know that according to Seebeck effect, if the two dissimilar metals are joined together, because of temperature difference between the two junctions, an EMF is induced. Okay, then that EMF E equal to A into delta theta plus B into delta theta whole square plus and so on. But this constant B is very small as compared to A, that's why that is negligible. Then you can write like this, E equal to A into delta theta. Now from this, what is delta theta here? T2 minus T1, change in temperature. Then A equal to E by delta theta. It's just like output by input. That's why it is also called sensitivity of thermocouple instrument. It's also called sensitivity of thermocouple instrument. But one of the main advantages of thermocouple instrument is it is used as a thermocouple instrument is it is used as a transfer instrument, and it is a true RMS meter. True RMS meter. And these instruments are having, because it is a true RMS meter and transfer instrument, these thermocouple instruments are having high accuracy also, but somewhat these instruments are having less overload capacity. That is only drawback. Remaining all our advantages are there. These instruments are less overload capacity And these instruments are used at RF range to measure the voltage, current and power at high frequency. Thermocouple instruments are more preferable. Special application is transfer instrument and it is a true RMS meter. Okay, this about the concept of voltmeters and ammeters. In the next session, we will solve some classroom workbook questions and I will give some summary points with respect to voltmeters and ammeters. With that, the chapter 4 will be complete. Okay, this about different types of instrument. One more instrument is also there, induction instrument, that you refer induction instrument in energy meter. In the discussion of energy meter, that I will discuss in detail about induction instruments also. Okay, that you concentrate. But here I am not discussing that instrument. With this, all the instruments are completed. In the next session, based on 4.3, 4.4, 4.5, we will solve some classroom workbook question. Then final some summary points I will give with respect to voltmeters and ammeters. Okay, thank you.